Hello again. This is my last dynamics video for you guys. We're just doing some more two-body diagrams. Well, in this case, it's a three-body diagram. And it's the same stuff, but with three free-body diagrams. Okay, so how many forces are on the left mass? Okay, so basically you got the weight and you got tension. Let's call that tension 1 because we got more complications here. So that's tension 1, and that has to be the same as this tension because of Newton's third law of motion. This is tension 2, and that has to be the same as this tension according to Newton's third law of motion. So we're doing the 16 kilogram mass. We see two forces acting on it. Oops. So that's the weight of mass 1, I guess. And so that'd be 16 mg, 16 times 10. That's 160 newtons. Tension 1, we don't know. So we'll leave it at that. Okay, let's do the middle card. I'm just drawing all the free body diagrams of all the objects. So the middle card has wheels. So there's no friction on it. We got T2. We got T1. I don't know which one's bigger yet. But probably the T1's bigger because look, 16 kilograms hanging compared to 8 kilograms on the other side. Okay, we also have normal force, but that's not going to matter. We also have weight too, but again, that's not going to matter because the normal force and the weight cancel out. Okay, let's look at free body diagram for object 3. We got T2. I'm doing this one. And we got the 8 kilogram. We got the weight. The weight is M3G. 8 times 10, 80 newtons. Okay, so there's your three body diagrams. How many forces are acting on the left mass? 2. How many forces act on the card? Well, actually 4, but only 2 are affecting its acceleration. How many forces on the right mass? 2. Are the forces on the system balanced? No, because this is more massive than this. So this weight 1 is bigger than weight 2. So it's going to move to the left in the direction of the bigger weight. Or forces. So I'm going to say no. What's the mass of the system? Okay, this M1 plus M2 plus M3. 16 plus 11 plus 8. So that's 35. So 35 kilograms. Okay, what is the size of net force on the system? Okay, so if I straighten this whole system out, there's the card. Remember, I like to straighten it out because that's what you can do that with pulleys. Okay, here's T1 and here's T2. T1 and T2 are not equal to each other. And then there's the weight here, weight 2. Oops, that's weight 3. 80. And there's weight 1. Weight 1 is 160. Okay, so what is the size of the net force on the system? Well, the T1 cancels out the other T1, the T2s cancel out. That just leaves one big thing. 80 that way, 160 that way. Okay, so net force on the system is equal to the total mass, 1 plus m2 plus m3 times the acceleration. Net force is 160 minus 80, which is 80 to the left. And so that'd be 35. So the acceleration is 80 divided by 35. I get 2.3 meters per second squared. Okay, so net force would be of the system is 80 newtons. And the acceleration of the system is 2.3 meters per second squared. What direction will the current move? Well, in the direction of the net force. The direction of net force is to the left. Now we could find the tensions in the string, either tension, but they're not asking us to do that, so I'll leave that. Oh, yes, it did. Over here. So what's the tension in the string? 1. Okay, so pick the easier of the two things. You're not going to pick the cart because it has 2 unknowns, T1 and T2. So pick the weight 1, the mass 1. So let's do that. So here's T1, here's 160 newtons, this is mass 1. Okay, so net force on system 1 is mass times acceleration. So 160 minus T1 is equal to the mass 16 times acceleration, which we found 2.3. 16 times 2.3, 36.8. So T1, we add T1 to both sides, then I subtract the 36.8. 160 minus 36.8. 160 minus 36.8, 123.2. Okay, then if I had to find the tension in, this is a tension in string 1 that I just found. Let's find this tension in string 2. Okay, so I'm going to take I mean, I could take the middle guy now. I could take the middle part. Okay, so I know T1 is 123.2 newtons from what I just did over here. Okay, so T2 I don't know, but I know F net is equal to the bigger one minus the smaller one. So that'd be 123.2 minus T2. And F net for the cart is MA. Mass of the cart is 11 kilograms. And the A is the same for all three objects because they're all connected by a string. Say it was 123.2 minus T2. T2 add to both sides is 123.2 minus 11 times 2.3. So that comes out to be minus 100.90. Okay. So this is the last question. Oh, and then we have some graphs stuff. Okay, so feedback diagram box 1. So these two tensions are the same. Okay, so we got tension 1, and then we got the weight equals mg 15 times 10, 150. Draw free box 2. Trickier. Okay, we got the weight pointing straight down. That's 35 times 10 mg, so that's 350. We got the normal force pointing up. Then we got the x component and the y component of the standard force. Okay, so this would be well, let's do it the other way. We have the x and y component of the weight. Okay, there's Wx, there's Wy. And we got tension pointing this way. We got tension pointing that way. Now, we also have friction. And I don't know what kind of friction. I don't know if it's static or kinetic, but I'll just draw it right here as friction. What's the maximum static friction between box 2 and the ramp? Okay, why did I put this friction that way? Because I'm assuming that it's going to be sliding up the ramp. Now, it could be sliding down the ramp. I'm not sure. Okay? So, what's the we'll figure it out later. What's this maximum static friction? So, Fs max equals U S times N. It's kind of annoying. N is equal to WY. Okay, this angle is the same as the inward angle right there. So this equals the adjacent side. So that'd be W2 times cosine of theta. Because it's not to the horizontal, so I have to flip the Q equation I gave you on the equation sheet. So this would be 350 cosine of 33 degrees right here. So that equals 293.53. Okay, so mu s is equal to 0.3 right there. Given. So 0.3 times 293. Is equal 88. So that would be the static friction. Okay, so letter E is box accelerating up or down the ramp. Explain. Okay. Well, first of all, I have to find what Wx is. So Wx is 35. Well, Wy was W2 cosine theta, so Wx is W2 sine of theta. 35 sine. 350 times sine of 33. 350 times sine of 33. 191. Okay, so that comes out to 191. 190.6 newtons. So, let's read the problem. Okay, while we're at it, find the kinetic friction if it's moving. So that'd be UK times N, which would be 0.20. Times 293.5. So that equals 58.7 newtons. The kinetic friction. If it was sliding, that'd be the friction, as opposed to the static friction. Okay, so is the box accelerating up or down the ramp? Okay, well let's look at this situation. Here's the box. Okay, here's Wx. W2x, the weight of the box, the x component of that weight. We already solved it as 191 newtons. Okay, it's connected by a pulley to a box that only weighs 150 newtons. So this force obviously is bigger than this force. So probably is going sliding that way down the ramp. And so the friction is going to be there. And that friction, I'm going to assume is sliding, is 58.7. Newtons. Okay, 191 minus 58.7 and 32 is 132. 132 is less than 150. So, see what I'm doing? 191 minus 58, 59 is 132. So this guy only has 132 pointing downwards compared to 150. So really it's accelerating up the ramp. Okay, because 192 minus 58.7, 191 minus 58.7 is equal to 132, which is less than 150. So I'm going to calculate friction acting on box 2. Well, I did that down here, 58.7 newtons, assuming that it's sliding up the ramp. So this is kinetic friction. It's equal to 58.7. I did that before. Okay, so let's find acceleration in the box. Okay, I'm going to straighten out this picture. So here's the box on the ramp. We got Wx equals 191. We got friction equals 59. I'm just going to round up.
Heidi Noyes.
So this friction is 58.7. Okay. Then we got tension. Those two tensions cancel out. Then we got the force of weight 2, weight 1, which we did right here, and is 150. So the net force on the system is equal to 191, 150 plus 59 minus 191. So I am getting 18 newtons up the ramp. Okay, so why is 150, 59 and 150 are in the same direction? So I take the bigger one, which is that, minus the smaller one, which is 191. So this is about the ramp. So F net equals MA. So 18 equals the total mass is 35 plus 15. 35 plus 15 times the acceleration. So acceleration is pretty small. 50, 18 divided by 50 18 divided by 50 is going to give me 0.36 meters per second squared. So that's pretty small acceleration up the ramp. Okay, so I did that. Solve for the tension in the string between the two blocks. So I'm going to pick the simplest one, which is the hanging weight. So that's 150. There's a tension. Same tension as on the block on the ramp. So F net for object 1 is equal to MA. So I know what's going up. So it's 150 minus T equals the mass, which is again 15 times acceleration, which is 0.36. So the tension is equal to 150 minus 15 times 0.36. That equals 145 newtons. Okay? So now we move to V versus T graphs. So this is just kind of a review on a V versus T graph. Acceleration is a slope. What's the car's acceleration in the first 20 seconds? It's 54, 30, so 20 is right there. So that would be 20. That'd be 20 over 20. I just found the slope positive. What's the net force applied by engine in the first 20 seconds? Well, the net force equals MA. So it'd be 2,300 times the A you just found. 1. So it's 2,300 newtons. See, from 20 to 40 seconds. Well, that's easy because there's no slope. So C is 0. Where's net force? Okay, let's let it be. Well, net force equals 0. If A is 0, net force is 0. Letter E, 40 to 50 seconds. Okay, so find the slope of that section, 20 over 10. So acceleration is 20 over 10, 2 meters per second squared, but it's negative. What's net force by from 40 to 50 seconds? Oops. Is equal to 2,300 times -2. It's -4,600 newtons. Okay, so all the rest of this is just explaining that graph. Okay, guys, this is the end of this gigantic chapter. So I will see you in person, hopefully, this coming week.